Type a question into Google, and an answer lands in your browser in a few hundred milliseconds. Behind that blink, your query races out across thousands of machines, digs through an index built from a meaningful fraction of the web, ranks the results with a pipeline refined over 2 decades, and reassembles an answer before you've finished reading it. That's not one clever trick. It's 6 systems working in sequence: crawling, indexing, ranking, understanding your query, serving the answer at scale, and keeping the whole thing fresh. Over the next few minutes we're pulling each one apart, using Google's own research papers, engineering blog posts, and even sworn courtroom testimony from a 2023 and 2024 antitrust trial that revealed more about how ranking actually works than Google ever chose to publish voluntarily. Before anything can be searched, it has to be found. Googlebot discovers new pages 2 ways: following links from pages it already knows, and reading XML sitemaps site owners submit directly. Every URL waiting to be fetched sits in a structure called the URL frontier, not a simple line, but a priority queue that reorders itself based on how important, and how often changing, a page seems to be. Crawling isn't free either. Google budgets it per site, balancing a politeness limit so it doesn't overwhelm a server, against its own demand for that content. And because so much of the modern web is built with JavaScript, Googlebot doesn't just download raw HTML, it renders each page in a real, headless version of Chrome, in a second pass, to see what a browser would actually show a person. Once a page is fetched, it's decompressed, parsed, and broken down into individual words, each tagged with its position, font, and formatting. In Google's original 1998 design, that word-level data gets inverted. Instead of storing, for every page, the words on it, the system flips it around and stores, for every word, the list of pages containing it. That's the inverted index, and it's still the foundational structure under nearly every search engine built since. Millions of pages online are near duplicates of each other, so before anything is indexed, the system canonicalizes, picking one representative copy and folding signals from the rest into it. And because a single postings list can run to millions of document IDs, they're not stored as raw numbers. They're stored as the gaps between consecutive IDs, then compressed further still, shrinking the whole index by a meaningful margin. For years, keeping the index fresh meant running enormous batch map-reduced jobs that reprocessed huge swaths of the web on a schedule, then swapped in a new index all at once. In 2010, Google replaced that with a system called Caffeine, built on a distributed transactions engine called Percolator. Instead of waiting for the next big rebuild, individual documents could now be updated and pushed live continuously, processing hundreds of thousands of pages in parallel every second. By Google's own numbers at launch, that single architectural change cut the average age of a search result by roughly 50%. It's a pattern that shows up constantly in distributed systems. Batch pipelines are simple to reason about, but incremental, transactional pipelines are what you build once staleness itself becomes the bottleneck. Larry Page and Sergey Brin's original insight wasn't about matching words, it was about trust. Imagine a random surfer clicking links forever, 85% of the time following an outbound link, 15% of the time getting bored and teleporting to a totally random page. A page's PageRank is just the probability that this endless random walk finds it at any given moment. Pages with more, and more reputable, incoming links get visited more often, and so rank higher. Computing that isn't done by simulation, it's solved directly with an iterative technique called power iteration, repeatedly passing rank across the link graph until the scores stop changing. And crucially, it's computed once, ahead of time, for the entire web, not recalculated for every search, which is exactly why it scaled, even in 1998. PageRank still matters, but it's one signal among a stack that's grown enormously since 1998, and for years Google kept most of the details private. Then, in the 2023 to 2024 US antitrust trial, Google's own VP of Search testified about the real pipeline under oath. First, retrieval and a system called RankEmbed pull a broad pool of candidates from the index using both keyword and semantic matching. Then Mustang, the primary scoring engine, applies more than 100 signals to narrow billions of documents down to a few hundred. A click-based system called NavBoost re-ranks those using 13 months of rolling click history, which results real people actually clicked on. Twiddlers, described internally as a kind of police force, nudge the ordering for things like diversity or freshness. And only the final 20 or 30 survivors get the most expensive treatment, a BERT-based deep model called DeepRank. Each stage costs more than the last, which is exactly why it only ever runs on what survived the one before it. Before your query ever touches the index, it goes through its own pipeline. Misspellings get corrected first, so a typo doesn't silently return nothing. Then the system expands your words with synonyms, search for gigantic shoes, and under the hood, it's effectively also searching for enormous shoes and huge shoes, widening the net beyond a literal string match. The hardest part is intent. A query like Jaguar could mean the animal, the car, or the old operating system, and with only 2 to 4 words to work with, there's rarely enough context to know for certain. That ambiguity is exactly why the later neural ranking stages matter so much. They lean on patterns learned from billions of past queries to guess what you actually meant, not just what you typed. No single machine holds the whole index, it's sharded across a huge number of them. So answering a query is fundamentally a scatter-gather operation. A root node broadcasts the query out to every shard in parallel, each shard searches only its own slice and returns its best local candidates. An emerging layer combines all of those partial rankings into the one list you actually see. That fan-out is what makes sub-second answers possible over an index far too large for any single machine to scan. But it comes with a catch: your response is only as fast as the slowest shard that answered it, and at this scale, on any given query, the odds that at least one of hundreds of parallel requests run slow are surprisingly high. In a widely cited 2013 paper, Google engineers Jeff Dean and Luis Andre Barroso named this problem the tail at scale. If even 1% of individual requests run slow, and a single query fans out to 100 machines, the probability that at least one of those 100 is the unlucky one climbs toward near certainty, meaning almost every user ends up waiting on someone's tail latency, even though almost no individual request is actually slow. Their fix is elegantly simple: hedged requests. If the first replica hasn't answered within some short threshold, fire off a duplicate request to a second replica, and just take whichever one comes back first, canceling the loser. It costs a little extra load across the system, in exchange for a dramatically shorter tail, a trade that, at Google scale, is almost always worth making. Freshness isn't one speed, it's two. The bulk of the web is recrawled on a rolling schedule, and how often any given page gets revisited is tuned to how often it's historically changed. A static reference page might wait weeks, a news homepage might get revisited within minutes. Layered on top of that is a fast lane for anything time-sensitive, breaking news, live scores, fast-moving stories, where being current is itself a ranking signal, and pages can be indexed within minutes rather than waiting their regular turn in the recrawl queue. It's the same tension every large system with a freshness requirement eventually runs into. You can't afford to treat everything as equally urgent, so you build 2 paths instead of 1. So how big is all of this, really? It depends entirely on which era you're asking about. Brin and Page's original 1998 paper described a system crawling on the order of 24 million pages, genuinely large for the time, tiny by today's standards. By the 2010 Caffeine launch, Google was processing hundreds of thousands of pages every second, and disclosed roughly 100 million gigabytes of storage. The most recent credible glimpse came from that 2023 to 2024 antitrust trial, which confirmed specific internal systems, like Mustang, applying over 100 ranking signals. But an exact current index size, or a queries per second figure? Google has never officially published one, and most of the numbers circulating online claiming otherwise are industry estimates, not confirmed figures. Given how this whole system actually works, that might be the most honest number of all, unknown, by design. Crawl the web, invert it into an index, rank it with a pipeline refined over 2 decades, understand what the person actually meant, serve the answer from thousands of machines in parallel, and keep the whole thing fresh. 6 systems, 1 query, a few hundred milliseconds. None of it is magic. It's the same distributed systems ideas you'll find anywhere at this scale: sharding, replication, incremental processing, hedging against your own slowest components. Google just happened to build one of the first systems that needed to solve all of them at once, for nearly every question anyone in the world might type. If you want to go deeper on any one stage, the source material is out there: the original PageRank paper, the percolator and tail at scale papers, and the antitrust trial transcripts. Thanks for watching.